Hello class and welcome to lesson 4.4 probability using counting techniques day 2. So today we're going to continue to use counting techniques, although we're going to give a little harder level of difficulty. All right, and we're going to be still focusing on probability. Okay, we will examine today a birthday problem. Okay, it's a classic combinations question, and the question is, what is the probability that two people in our class have the same birthday? Okay, so let's pretend for a moment that we don't have twins in our class. Now, the last couple of years I did teach this, folks. I did have twins in my class, so it was pretty hard to do this example because we did have twins. And we also want to make sure that nobody has a birthday on Feb 29th because that deals with a leap year. Okay, so subjective probability, I just would ask the class if I was in class and say, hey, what do you think the probability is of someone being in the class, okay, that has the same birthday? Well, maybe a 1% chance. Some people might say 2. However, if we knew we had twins in the class, some people would say, hey, subjectively, I already know it's 100% because we have twins, but we're not going to pretend we had twins. So it's going to be a pretty low percentage. Subjective is giving your opinion, okay? Your intuition and experience. We know it's going to be low, okay? Now we're going to take a look at what is the theoretical probability of this. Well, first of all, we have to figure out and just remember how many days there are in a year. So each year has 365 days in a year. Okay, and it's going to depend on the number of students and teacher in the class. So let's just do the example of there being 19 total. Okay, so that's going to be 18 students. Okay, plus me, the teacher. Because I'm still included and I still have a birthday. Okay, so the event that we want, guys, the event where the outcome we're looking for is that two people have the same birthday. Okay? And in some cases, when we do counting techniques, folks, it is easier to do the opposite or the indirect method, and that's what's going to happen in this case. So A prime means that nobody has the same birthday, and that's what we're going to do in this case. Okay, and the reason we're going to use this, the reason we're going to use the complement is, or the indirect method, is because it's easier, in this case, to use complement method. Awesome. Okay, so now we're going to find out the number of ways that this doesn't happen. Okay. So number of ways that the complement, meaning nobody has the same birthday, is. Okay. So we start with person 1. We're going to times it by person 2, times it by person 3, and times it by person 4. Now I'm going to set this up with values, so just give me a second before you see it. Okay, so person 1, it doesn't matter who we start with, they could choose any of the 365 days of the year. Okay, cool. Then I'm going to go to person 2 because they can't have the same birthday as the first person. That person, he or she, has 364 days left. Okay, times the third person, again, you're going to see the pattern here, 363. Times 362, ... We're going to go all the way till we have person 19. Okay. All right. So what we're going to do here, folks, is realize that we're subtracting 1 each time, so we can set this up, okay, as 365 permutate 19. Okay, because we need 19 of them. Okay, all right. Now, to figure out the number in our sample, Okay. Well, person 1, they can pick any 365 days, times person 2, out of a total, it can be any 365 days, times person 3, etc. Each of them have 365 days, and we would times that all the way to person 19. Okay? So when we take a look, folks, the base stays the same. We're going to multiply it by itself 19 times, so it's going to be to the exponent 19. All right, so now we have the rough information. Now we're going to do the probability of this not happening, and then we'll relate it to the complement method. We'll put it back to the regular method. So the probability of this not happening, okay, is the number of A prime over the number in our sample. Okay, number in A prime equals 365 permutate 19 divided by 365 to the exponent of 19. Okay? And ladies and gentlemen, don't try to write the numerator and the denominator. Just plug it in your calculator. Otherwise, you're going to have big, big numbers. And the answer is going to be 0.62. Okay? Which really represents a 62% chance that it won't happen. Okay? That's not what the question asked, though. The question asked what's the probability of the event happening. So of them having the same birthday. So that becomes 1 subtract the probability of the event not occurring, which is the opposite. So it's going to be 1 subtract 0.62, which equals 0.38. So therefore, to answer this question, there is a 38% chance of same birthday. Now I want you to make sure that you know how to do this, folks, because hint, hint, you might see one of these on your unit test. Quite often I use one of these as an example. Do you understand how to set this up? Okay? So that is the theoretical probability. Okay? And if I say let's figure it out, I would take everybody in the class. I would say, hey, whoever's January 1st, you're at the front of the class. Whoever's in December 31st at the bottom of your class, at the back of the room, and we'd line up in order. Okay? And this would be the experimental probability. And we would find that out. Okay? Also called empirical prob. Okay? And if we lined you up, hopefully we realize that it's 0% because it doesn't happen. Okay? If we did have twins in the class, then it'd be 100%. Okay? Or if we had someone who shared the same birthday who was not a twin, just born on the same day. All right, so please make sure that for the birthday problem that you write down here, study for test somewhere. Okay, make sure you know the difference between the number of outcomes we're looking for, so study this. And how to find the number in our sample. Okay, so that's the birthday problem. That's a classic probability problem, and don't be surprised if you see one on your test. Okay. Just remember that it varies depending on the number of students that you have in a class, and the probabilities change with each number increasing or decreasing in the population. Okay. Because remember, the higher the number, the greater the chance, right, that someone would share the same birthday. All right, example 2. What is the probability of being dealt a full house? This is a poker hand from a standard deck. Now, I'm not trying to turn you into gamblers, but this happens quite often if you want to take a look at this. Okay, so first of all, a standard deck, hopefully you remember that a standard deck has 52 cards. Okay. A poker hand, folks, a poker hand means that you know you need 5 cards total. Okay? And a full house, let's take a look what a full house is. So it's 2 of one number, or face card, doesn't matter. Okay? And 3 of another number. or face. I'll put down face because you can have like 3 jacks. Okay? All right. So we want to eventually find the probability out. Okay? And don't forget that when we take a look at our sample, that we need all 5 card hands. Okay? So to find the number in our sample, you take 52 cards total, and we're going to choose any 5 of them. Okay, just to get, doesn't matter which 5 we choose because all total possible, order is not important in this case. Plug that in your calculator. We're going to get 2,598,960 ways that you could get 5 cards. Okay, people who make a living off of playing poker or whatnot, they know these probabilities. They know their odds. They've got things figured out. Okay, now, what is the number in our outcome? So the event we're looking for is the full house. So what did I say? It was 2 of one and, or times, 3 of another. Okay, so if I take 2 of one number, well, in a deck, how many total numbers can you have? So how many 4s are there in a deck? Well, there's 4. So we're going to take 4 and we're going to choose 2 of them. Okay, but we also have to take 1 card that's different. Okay, so there's 13 cards and we're choosing 1 other suit. Okay. Sorry, I apologize. There's 13 other cards from a different suit and we're choosing 1 card. I apologize. I said that wrong. Okay, now 3 of the others. So we're going to take a look at 4, choose 3. Okay, times 3 of another. Okay, so we need 12, choose 1. Okay, because it has to be of another number. So that's why it's instead of 12, instead of 13, it's 12, because it needs to be another face value or card value. Okay. And so just backing up, this 13 here, that tells you that there's 13 different possible doubles you could have. Okay? All right. So let's plug this in our calculator, folks. Okay? So 4 choose 2 is 6 times 13 choose 1. You don't need your calculator for that. You should know that. Times, which means and, right? Okay, 4 choose 3, you should know that's 4, times 12 choose 1, which is 12. If you plug that all together, there are 3,744 ways. Maybe you didn't know that, maybe you did. Okay, poker players know that because that's a high standard of cards. Okay, in terms of poker order. Okay, now we got to finish off the probability. So probability of A equals the number of A over the number in our sample. Okay, so number of the outcomes, so how many ways we can get a full house is 3,744 divided by how many possible ways can we get 5 cards from a deck of cards? 2,598,960. Okay, plug this in your calculator, folks, and you're going to get a small number, and hopefully you realize that when you're playing cards, the odds of getting things are low. Okay, so that equals 0.14% chance. Okay, so therefore you have a 0.14% chance of getting a full house. Okay? All right, folks. Hopefully you enjoyed that. Remember, that birthday problem will be part of your review section, and please come see me if you need help with that. Here's your homework, guys. Page 324, numbers 2, 9, 10, and 15. Have a great day, and as always, come see me if you need some help. Ciao, Bella.